Hey, Allie. So we've been looking at how a matrix can give us a linear map, but the notes say we're going to flip that idea on its head today. The big question is, given a linear map, can we find a matrix for it?
Oh, yeah, that's what I was wondering about. It feels like it should be yes, right? A matrix is just a way to do a linear transformation.
Exactly. But the notes are a bit more careful about it. Let's see what the next page says. Okay, so the notes give us a no and a yes. The first answer is no. The linear map F from V to W by itself cannot determine an associated matrix A.
Why not? What does that actually mean?
It's like the linear map is the abstract idea of the transformation, but a matrix is a specific set of numbers. To pin down those numbers, we need a reference frame. That's where the yes answer comes in. If we fix a basis of V and a basis of W, then we can find an associated matrix A. So we need to set up a coordinate system first.
Okay, that makes sense. Like, without a basis, we don't know how to represent the vectors, so how could we represent the transformation? That's what a basis does, right? It gives us a way to write everything down?
Right, and the notes are very specific about that. Let's look at the conventions on the next page. It says, let B, V equal V1, V2, Vn be a basis of V, where n equals dim V, and let B, W equal W1, W2, Wm be a basis of W, where m equals dim W.
Okay, so we're just setting up our coordinate systems for the starting space V and the ending space W. Okay, I'm with you so far. What do we do with them?
The next page shows us the core idea. It says, for each Vj in BV, f of Vj in W can be expressed as f of Vj equals A1jW1 plus A2jW2 plus plus AMJWM.
Wait, why are we looking at what the linear map does to the basis vectors?
Think of it this way. Since the basis vectors of V can create any other vector in V, if we know what the linear map does to them, we know what it does to every vector. And because the result, f of Vj, is a vector in W, we can write it as a combination of the basis vectors of W. These coefficients, the aij's, are the key.
I see. So the aij's are like the numbers that tell us how the basis vector Vj gets transformed and expressed in the new space's basis.
Exactly. And that's what makes the matrix. The notes say, using these coefficients, aij, we can formally write f of V1, comma, f of V2, f of Vn equals W1, comma, W2, comma, Wm times A. Then it defines the m by n matrix A as the matrix representation of F with respect to the bases BV and BW. Each column of A corresponds to the coefficients for one of the transformed basis vectors, F of Vj.
Whoa, that's really neat. It's just a table of the coefficients that describe the transformation. Okay, so we found the matrix. Can we see an example based on a linear map that's not just multiplying by a matrix, like the differential operator on the subspace spanned by sine and cosine?
That's a perfect example. Let's use the example from the notes. Our vector space, W, is a subspace of the set of real-valued functions on R, spanned by a basis B equals sine x cosine x. Our linear map, F, is the differential operator, d by dx. Since the derivative of a function in W is still in W, the output space is the same as the input space.
Okay, so we're using the same basis, B, for both the domain and codomain.
Exactly. Now, we apply the linear map to each basis vector of B, one at a time, just like the notes describe. Let's start with the first one, V1 equals sine x. What's its derivative?
The derivative of sine x is cosine x. So d by dx of sine x is cosine x.
Right. And how do we write cosine x in terms of the basis of B, which is sine x cosine x?
That's just 0 times sine x plus 1 times cosine x.
Perfect. The coefficients 0 and 1 form the first column of our matrix. Now, for the second basis vector, v2 equals cosine x, what's its derivative?
The derivative of cosine x is negative sine x.
And how do we write negative sine x in terms of the basis of b?
That's negative 1 times sine x plus 0 times cosine x. The coefficients are negative 1 and 0.
Exactly. So we've got our two columns. The matrix representation for the differential operator on this space is the 2 by 2 matrix. 0, 1, negative 1, 0. See? We use the exact process from the notes to turn a linear map into a matrix.
That makes a lot more sense now. I can see how the matrix is just a way to encode the transformation's effect on the basis vectors. Now I get the idea. But is the matrix representation we get, is it the only one?
That's the next big question. Let's turn to page 8. Theorem 1 says, for a linear map F from V to W, there exists a unique matrix representation A with respect to the given bases BV and BW. The keywords are unique matrix representation.
How do they prove that? I'm not sure why it has to be unique.
The proof starts on the next page. It starts by assuming there are two different matrices, A and B, that both represent the same linear map. It says, suppose that there is another matrix representation, B equals Bij, with respect to BV and BW. And then it sets up the equation we just saw, but with B instead of A, and says that the two must be equal.
Okay, so A and B both describe the transformations, so they should be equal.
Right. And then it gets to the cool part on the next page. For each column, j equals 1 to ... n of the above equation, we have a1j minus b1j times w1 plus a2j minus b2j times w2 plus ... plus amj minus bmj times wm equals 0. The proof then says since BW equals WI is a basis, it is linearly independent. Thus, A1J minus B1J equals A2J minus B2J equals ... equals AMJ minus BMJ equals 0.
Wait, why can we say all those terms are 0?
Remember what linearly independent means. It means the only way for a linear combination of the basis vectors to equal the 0 vector is if all the coefficients are 0. So since we have a linear combination of the basis vectors of W that equals 0, the coefficients must all be 0. And if Aij minus Bij equals 0, that means Aij equals Bij.
Wow, so because the coefficients have to be the same, the matrices A and B have to be the same. That's a super elegant proof. I love it when they use linear independence like that.
Me too. And then there's a final theorem on page 11 that shows the other direction. Theorem 2 says, for any m by n matrix A, there exists a linear map F from V to W such that its matrix representation with respect to given bases BV and BW is A.
So basically, any matrix can be thought of as a linear map as long as we define our bases.
Yep, and the proof shows us exactly how to do that on the next page. We can define a linear map, F from V to W, by f of Vj equals the sum of I equals 1 to m of Aij times Wi. So we just defined what the map does to the basis vectors based on the matrix coefficients. Then, since the map is linear, we know what it does to any vector in V.
Okay, so that means we've created a perfect back and forth between linear maps and matrices, as long as we pick our bases. That's a huge deal.
Right? And that's what the conclusion on the last page sums up. How do you represent a linear map F from V to W as a matrix? Fixing bases of V and W, the matrix representation is given by, and then it shows the big matrix equation we saw earlier. And then, is the matrix representation unique? Yes, once we fix the bases, but we get different matrix representations for different bases.
So the matrix is unique for a pair of bases, but we can have a different matrix for the same linear map if we change the bases. That's a really important distinction. It makes me wonder, what if we change the bases, would the two matrices be related in some way?
That's a great question. I bet we'll cover that in a later lecture. For now, I think I get this part.
Yeah, I feel a lot better about it now. Let's grab some coffee before the next class.
Sounds like a plan.